So now that we have covered the introduction to VSEPR theory and all of the 5 different types, 2 electron groups, 3 electron groups, 4, 5, and 6 electron groups. So the 5 different types of electron group geometries, which is how those electron groups arrange. So we had linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. That's always the baseline. You have to start with that. How do those electron groups orient? Then to get the molecular geometry or molecular shape, we look at all of those 2, 3, 4, 5, 2, 3, 4, 5, or 6 electron groups and go, okay, are there atoms on the other end of that electron group, making it a bonding group? Or is there not an atom on the other side, making it a non-bonding group? Is it a lone pair or a free radical electron? Well, that really makes a difference, because if all the electron groups are bonding groups, that means there's an atom on the other side, which means the arrangement of atoms would be exactly the same as the arrangement of the electron groups, which would mean the molecular geometry would be the same as the electron group geometry, right? Because molecular geometry, we're looking at the atom, the arrangement of atoms about a central atom. The electron group geometry, you're looking at the arrangement of electron groups around the central atom. If those happen to be the same, they'll have the same, right? That's pretty easy. But what if you've got any non-bonding groups, lone pairs or free radical electrons? That means the arrangement of atoms about the central atom are not the same. It's not the same as the arrangement of the electron groups. You've got some hanging electron groups which push atoms around, but there's no atom there. So in that case, if there's any non-bonding groups, the molecular geometry is not the same as the electron group geometry. So that provides us a whole bunch of subsets, right? So say we have 4 electron groups, you're going to have a whole lot of subsets on whether some of those are, is one of them non-bonding, is 2 of them non-bonding. It creates these subsets of molecular geometries based on each electron group geometry. Let's start hacking through. There's a lot of them. I don't know if I'll get through them all in this video, but let's at least get 2, 3, and 4 electron groups, which you probably covered in high school or introductory chemistry. If we can do 5 and 6 with the expanded, 5 and 6 electron groups have to be expanded octets. If we can fit them in this one, great. If not, we will do the 5 and 6 electron groups in a second part 2 video on these molecular geometries, and then we'll do complex molecules where we have lots of central atoms. Oh boy, oh boy, oh boy. Let's again start simple and get tougher. Let's start with the 2 electron groups. Only one option. There's no subsets to this. If you have a central atom with 2 electron groups, right, they both have to be bonding, because if it wasn't, it wouldn't be a central atom anymore, right? Like a diatomic molecule, if you only had 2 atoms in there, it's automatically straight. It's linear, but there's no bond angle. So you have to, if you have 2 electron groups to apply VSEPR, they both have to be bonding groups, which means the electron group geometry and the molecular geometry are the same. So they're both linear, and you would have a 180-degree bond angle, right? Alpha being the notation for bond angle. For example, right? If you have HCN, I'm not going to go through and do the 6n plus 2 stuff. You could practice that if you want to. But if you have that carbon's the central atom, right? It's got an atom on either side. It's a triple bond to the nitrogen, so that's 1 electron group. Got a single bond to the hydrogen, that's a 2nd electron group. Right? That lone pair is on the nitrogen, not the carbon. So you have 2 electron groups, 2 regions of electron density, a triple bond and a single bond. That makes it linear with a 180-degree bond angle. Woo-woo! Let's go to the next one. Let's go to 3 electron groups, all of those electron groups being bonding groups. See if you can do it yourself. Here's a look at 3 electron groups. Hopefully you got this. All 3 of them bonding groups. In that scenario, the electron group geometry and the molecular geometry would be the same, because the arrangement of atoms and the arrangement of electron groups are both the same. So they're both going to be trigonal planar. So you have some central atom with the blue being the electron groups and the X being atoms on the other side, giving you 120-degree bond angles. All of them are 120-degree bond angles. For example, let's say we had carbon with a double bond to sulfur with a single bond to hydrogen, single bond to fluorine. Look at the central atom, the carbon. So this is a simple molecule. You've got a single bond, that's 1 electron group. Another single bond to the fluorine, that's a 2nd electron group. A double bond to sulfur, that is a 3rd electron group. 3 electron groups with an atom on the other side, they're all bonding. Boom. Right? 120-degree bond angles. What if one of these was a lone pair or a free radical electron? Oh, it ain't going to be trigonal planar anymore. Let's look at 3 electron groups, but 2 of them bonding, 1 being non-bonding or a lone pair. See if you can figure that one out. All right, did you get this one? So let's say we have 3 electron groups again, so 3 regions of electron density. Oh, I forgot to erase this. Hold on, where'd my eraser go? It's gone. Hold on 1 second. I lost my eraser. I found my dirty, stinking rag. This is almost 300 videos. Ugh. This used to be, I think, white. Were that? Getting Brad. Every once in a while, I just kind of racing, I flip it around. Like, I couldn't find it. It took me like a minute to find it. All right, so 3 electron groups, 2 bonding, 1 non-bonding. I'd forgotten to erase the structure from the other one. So here's our 3 electron groups, but 1 non-bonding. We'll just say it's a lone pair, but that could be a free radical electron. And then we got 2 atoms on the other side. Well, the atomic arrangement's different than the electron group geometry. That is a trigonal planar electron group geometry, but we don't see that. There's no atom there, so this is the remaining structure. Do you see that? That's the remaining structure right there. Looks like a little bat, right? That's what they call bent. I've also seen V-shaped or angular. I've seen different types of things, but the most common one I see is it's bent, right? So you pop that lone pair up there. Ozone being a prime example, where you got the 3. I think we did ozone when we did resonance. So that's technically a resonance structure, but you get the double bond, that's 1 electron group. The single bond, that's 2 electron groups. The lone pair or non-bonding group, that's 3. Gives you a trigonal planar arrangement, so always draw that, and then boop, pop the lone pair in there. What's left is bent, so you've got the 120-degree bond angles there. Not too bad. And that's as far as we can go here, because if we did another lone pair, then you wouldn't have a central atom anymore. So we're done with the 3 electron groups. Let's get to the 4 electron groups, and the more electron groups you have, the more sub-types of molecular shapes you can run into. So let's go to 4 electron groups, all bonding groups. 4 electron groups. Now remember, if they're all bonding groups, then the atomic arrangement about the central atom is the same as the electron group arrangement. So the electron group geometry, which was tetrahedral, will be the molecular geometry, which is also tetrahedral. So if you want to draw that 3-dimensional shape with the 109.5 degree bond angles on a 2-dimensional surface, you need that dash wedge structure. So it would look something like this, right? So imagine the greens are chlorine, the black is carbon, and these are the hydrogens. So I'd grab a chlorine, grab it like that, put another chlorine. These are in the same plane. Thus you have the lines. See the 109.5 degree bond angle? Then you got this hydrogen coming out at your face. That's the solid wedge. And there's the hydrogen coming away from you towards my face. And that's the dashed wedge. Everything's 109.5 degree bond angle. So that's a tetrahedron or a tetrahedral shape. And of course, I could have put these, I could have oriented it any way I wanted. Put the chlorines over here, chlorines over, doesn't matter. So CH2Cl2, tetrahedral, 109.5 degree bond angles. Makes a big difference. That's not what the Lewis structure looks like. Let's see if you got this one. So we're going to do 4 electron groups again. So we're going to have that tetrahedral electron group geometry, right? But 3 of them will be bonding with an atom on the other side, and 1 will be non-bonding. So you'll have 3 atoms, and the top will be a lone pair. So if we take the original tetrahedral electron group geometry and boop, we can't see that lone pair on top. This is what you're left with. Looks like some kind of virus or something. Put your payload in there. So that's not, it looks trigonal planar sort of, but it's not flat. See, it's not 2-dimensional. So it's not trigonal planar. It's trigonal pyramid, right? Do you see that? So you form this pyramid with a 3-sided base. Tricky, because that lone pair pushes those 3 bonding groups down out of a planar arrangement. And lone pairs actually take up more space. They spread out. Right? It's like when you're sitting in an airplane, the middle airplane seat, right? You're like, you're smashed in there between the 2 people. And then if somebody gets out and goes to the bathroom, you're like, you kind of spread out. That's kind of what a lone pair does. It just goes, and the electrons just kind of spread out and push a little more. So it pushes those down. So the angle you'd think would be 109.5 degrees based on the tetrahedral electron group geometry. But it turns out it's a little bit less. So I just put like approximately 109.5. A lot of people just say 109.5. It's really closer to about 107, depending what the atoms are. You know, about 2.5 degrees less than you'd think, because that lone pair has more repulsion. So a lone pair or a non-bonding group repulsing a bonding group has greater repulsion than a bonding group with a bonding group. And then two lone pairs are even worse. They're like, there's only two people next to each other in the airplane that don't want to be next to each other. So ammonia is a prototypical one, right? So ammonia has 4 electron groups, but one's a lone pair and 3 are single bonds to the hydrogen. So single bond, single bond, single bond, lone pair. That's 4 electron groups. Tetrahedral arrangement. Top one is it doesn't really matter, but you can see it best when you put the lone pair on the top. Then you can see the trigonal pyramid arrangement here, right? So I got the nitrogen, I got the hydrogen coming out this way in the same plane, that's the line. This hydrogen's coming at your face, that's the solid wedge, and this hydrogen's coming away from you towards my face, that's the dash wedge. And we'd say about 109.5 or a little less than 109.5. Not too bad. Now we could get another electron group on here, another non-bonding group. So let's do 4 electron groups, 2 bonding, 2 non-bonding. Let's see what we get. Let's do some agua, my friends. Let's do 4 electron groups, 2 are bonding, 2 are non-bonding. So you got your central atom, you got your 4 electron groups in a tetrahedral electron group geometry, but 2 will be connected on the opposite side by atoms, so those are bonding groups. And then you got 2 lone pairs. Now, it doesn't matter where you put those 2 lone pairs, but I tend to put them where the dash and the wedge would go, so you can see the resulting bent structure. So for example, let's say, let me get the tetrahedron here on my little model set. I'm a model, you know what I mean. So that's the tetrahedral arrangement, but we have 2 lone pairs. Pop. So I like to orient like this. So here's your wedge and your dash. Pop, pop. That's what you're left with. So you see that's flat, that's 2-dimensional. So that's bent. So we have 2 situations where you can get bent. 3 electron groups, 2 bonding, 1 non-bonding, or 4 electron groups, 2 bonding, 2 non-bonding. Both give you bent, but the angle's a little different. Remember when we did the 3 electron groups with 2 bonding and 1 non-bonding? That was about 120 degrees. So this bent has a smaller angle because those 2 lone pairs are really pushing. Because those lone pairs repulse so much more, so they push them a lot closer together. So we say around 109.5, really about 104.5. Every lone pair kind of drops at about 2.5 degrees. So you go from 109.5 to 107 to 104.5, roughly, give or take. Now, look at the difference between water as far as the VSEPR or the dash wedge or VSEPR structure versus the Lewis structure. Lewis structure looks linear, doesn't it? But see, the Lewis structure doesn't account for shape. It's just the types of bonds and the connections, right? Huge difference, because if water was straight, it would change its melting and boiling points, and water wouldn't exist on this planet, and life probably couldn't exist, right? Whereas the actual structure is bent. So this is what we call the VSEPR structure or dash wedge. I like to call it the VSEPR structure. It's just drawing the Lewis structure in the proper 3-dimensional molecular shape or molecular geometry. So here, if I put the lone pairs where the dash and the wedge would normally go, it doesn't look like a dash wedge structure, but technically it is. So you'll hear me call it a dash wedge structure or VSEPR structure. All it is, Lewis structure in 3 dimensions. Draw the bond angles. Boom! There's our water. You flap, flap, flap away, little bat. Let's do, well, that means this is everything that follows the octet rule. We can't take any more because it wouldn't be essential atoms. So we can't do any more lone pairs on that. So we're done with the 2, 3, and 4 electron groups. We only have 5 and 6. I was going to do them in a separate video, but I think I can finish them on this one. Let's do it. All right, let's get into the expanded octets. 5 electron groups now, right? Which requires an expanded octet. All of them bonding. Therefore, the atomic arrangement and electron group arrangement's the same. So the electron group geometry of trigonal bipyramid will be the molecular geometry of trigonal bipyramid, both. So you got the central atom. Remember, you've got the 2 axial positions, right? Kind of like the axis of a top, and you can spin it. Whee! Oh, you couldn't see it. So this spins, it rotates like a top. And then you've got the equatorial positions with a triangle, right in the center there. So you've got the 120-degree bond angles in the equatorial positions and the 90-degree between the axial and equatorial. So you get the 2 different bond angles there. Example, PCl5. So if the blue is phosphorus and the greens are chlorine, right? You can see that arrangement there. So the way I draw it is I draw the phosphorus with the chlorine on top, chlorine on bottom. There's the axis all on the same plane. I rotate it so that the one to the right is also in the same plane. So I draw the line. This one's coming out at your face. That's the open wedge. And this one, the back of the equatorial, is coming out away from you. So that's the dashed wedge, right? 120, 90. There you go. You can orient it any way you want. I just like to grab it, orient it so I can see that one to the right and then the dash and wedge on the left. I do it the same way every time, so I never have to, if I'm on a test, I'm like, which way should I hold it? And I waste 2 minutes trying to figure it out. I just go boom, boom, good. Boom, boom, good. Boom, boom, good. Same way every time. Same with the tetrahedron. Same with octahedral. All of them. So let's take one of these and make them a lone pair next. So we'll have 4 bonding groups and 1 non-bonding group. What are we going to get? This next one is possibly the trickiest of them all. So we're on number 8, right? So we got 5 electron groups. 4 are bonding and 1's a lone pair or a non-bonding group, right? So you got your central atom, you got your axial positions, your equatorial, so you got a trigonal bipyramid electron group geometry, but that's not going to be the name of the molecular geometry because we have one that's not a bonding group. So the way this pans out, if you look at it, so here's our trigonal bipyramid, right? So what you do, now we have an asymmetry. Where does the lone pair go? That's the tricky part. The lone pair could go in an axial position or it could go in an equatorial position. So in the axial position, it's smashed with these 3 90-degree angles on the equatorial spots. If it went equatorial, you got the 2 90s, but these other ones are way over at 120. So there's a wee bit more space in the equatorial positions, and lone pairs will always go where they have a little more space, more room to spread out. So lone pairs, when you're talking about a trigonal bipyramid electron group geometry with 5 electron groups, always go in the equatorial spots. Always. So I'm going to put my lone pair. So if I set up my stuff, I'm going to put my lone pair in one of these equatorial. Pop. And that's what you're left with. So I just put it on this side right here. Boop. So we got a lone pair there. We got the wedge coming out at you. We got the dash wedge going away from you. One straight up. For example, SF4. So if the blue's a sulfur and the greens are fluorines, we're not color coding anything properly, right? You can see it just like that. Then the shape's a little tricky. What do we call that shape? Because it isn't trigonal bipyramid because we're missing this one. So what if we went like this? And it looks like something in my backyard because I have 4 kids, 3 daughters and a son. So if I put a daughter and a son here and a daughter and a son here, and they go herky, 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 and they teeter-totter back and forth. What's that called? It's called, instead of a teeter-totter, it's called a seesaw. So this is called the seesaw shape. You gotta love that. So what you can do is you just tip it over. So where we have, so just flip this over that way. So you have the A here. Now the axial positions across the top here like that, and then you have, when it comes down here, the wedge is coming out at you and the dash is going away from you. A lot harder to draw in the lone pair. So very, very hard to draw this. That's why I like to leave it like this. Just draw the trigonal bipyramid, put the lone pair there. But really it's easier to see the shape when you do this. But how do you draw that? You can you see this chlorine? There it is. Went bye-bye. There it is. It went bye-bye. So really hard to draw that. So I like to keep it like this, but you can see why it's called seesaw, because when you tip it over, it looks like a seesaw. That's pretty cute, right? So it creates a new bond angle though. So we still have the axial to equatorial bond angle of 90 degrees. We still have the equatorial to equatorial of 120. But now that we put that lone pair, now we've got axial to axial. You've got 180-degree bond angle. So you actually have 3. This, I think, is the most complicated structure. The main thing is, when you're adding lone pairs to something with 5 electron groups, they always go in the equatorial position. There's extra space there. Otherwise, you get the wrong structure. 5 electron groups. Now let's add another non-bonding group. So 3 of the 5 groups are bonding and 2 are non-bonding. Right? So obviously the atomic arrangement about that central atom is not the same as the electron group arrangement. So it's not going to be, the electron group arrangement is trigonal bipyramid, but 2 of them are lone pairs. So 1 goes in an equatorial, pop. A second one also goes equatorial because there's more space, and you're left with this. Now I like to put the 2 lone pairs where the dash and wedge would have gone. So it makes it flat. Do you see that? So it makes it two-dimensional or planar. Now, you have this 90-degree angle between the axial and equatorial, but there's no more equatorial, but you do have axial, so you got the 180 as well. So you got the 90 and 180. So chlorine trifluoride is an example with the chlorine in the middle. You got the fluorine, just like so. See the 90 degrees, 180. Now, what's the shape of this puppy? Well, it's just like when we did the seesaw. It's kind of hard to see. Well, what if I did this? What letters that look like? Oh, it's T-shaped. So if you tip it over like this, you get the A with the two X's here. So the axial then becomes flat across, the vertical becomes horizontal, and then you get this one coming down like that. And then you've got the two lone pairs like so. So you can see the letter T. Boop, T-shape. One of my favorite characters of all time. Hey, boy! From the A-Team, Mr. T. I actually, when the navigation first came out, I don't like my computers talking to me and stuff, but so if I wanted to get one, I got one that had the sound of Mr. T on it. It was so cool. So I'd be driving around, and it's like, hey boy, take a left up here. And I'd miss it on purpose. It's like, yo, fool, you missed your left-hand turn. Now you got to do a U-turn, fool. And it was just so awesome. And I had it on my phone. So when it rang, I would purposely not answer it, because it would go to voicemail and say, hey, fool, you missed a call. If you don't know who Mr. T is, I'm so sorry. You're missing out one of the greater things in TV history. Yay, Mr. T. I love him so much. He's so awesome. Dun, dun, dun. Now, we could put another lone pair here. Boop, boop, boop. Let's do 5 electron groups, but 2 bonding and 3 lone pairs. See if you can figure out what that looks like. 5 electron groups. 2 are bonding, 3 are non-bonding, okay? So 5 electron groups gives you a trigonal bipyramid electron group geometry, but we have 3 lone pairs, right? So take the first one out of the equatorial position, gone. Second one out of the equatorial position, gone. Third one out of the equatorial position, gone. What are you left with? A straight line, my friends, right? Just the axial positions. So you've got lone pair, lone pair, lone pair. There's your 3 non-bonding groups. Atom, atom, there's your 2 bonding groups. There's no more equatorial spots left. Look at that. You just got a straight line. So the triiodide, which we did before when we did expanded octets, when you do the Lewis structure, right? I didn't draw the Lewis structure, but this is the result of that. So if we did the Lewis structure, you'd have this, complete your octets on the iodines on the outside, but you had that expanded octet here. So this is the Lewis structure. So if you do your 6n plus 2 minus the valence electrons, you get a value of -2, which is why you have the 10 electrons around the central iodine. Well, that gives you 1, 2, 3, 4, 5 electron groups around that central atom. 3 are non-bonding, 2 are bonding. Boom. So in the VSEPR structure, you don't have to do the brackets and the charge, only the Lewis structure. Technically, in the VSEPR structure, you don't have to draw any lone pairs. I like to include them on the central atom, but the terminal atoms, you don't have to. Lewis structure, you have to have all the lone pairs. The VSEPR structure, you do not, although it helps to put them on that central atom so you can see the resulting linear shape. But because in the VSEPR structure, you're just looking at the atom arrangement. That's it, right? It's a little bit more simple than the Lewis structure. That's as far as we can go, because if we did one more lone pair, we wouldn't have a central atom anymore. So we now have to go to 6 electron groups. See if you can do 6 electron groups all bonding. See what shape you get. All right, we're on our 11th one. We're only going to do 13, lucky 13. We're almost there. You feeling a pattern, though? Getting kind of redundant. And yes, you have to memorize. There's only 13 total. And 2 of them are the same. There's 2 bents, so there's really only 12 shapes. I mean, that's nothing compared to, like, anatomy. 800 trillion bones in your head or something. All right. So 6 electron groups, all bonding. That means the arrangement of atoms around the central atom is the same as the electron group arrangement. So the electron group's geometry, which is octahedral, is the same as the molecular geometry, which will be octahedral. So you have your central atom, like we had octahedral, central atom, and you have the one up, one down, and then you have a square around the middle, right? You don't really have axial equatorial anymore because this is so perfectly symmetric. So that's how that looks. Can you see how everywhere I look, every single angle is 90 degrees. Everywhere you look, it's a beautifully symmetric, super expanded octet, man. This takes 6 electron groups. That's 12 electrons. So you're going to have a 6n plus 2 minus number of valence electrons equal to -4. So 4 electrons beyond 8 gives you 12 electrons. That's the only way to accommodate 6 electron groups. Gotta love expanded octets. They give you the really cool shapes, like Mr. T. It's not Mr. T shape, it's T shape. I just like Mr. T. All right, here we go. So sulfur hexafluoride, right? Commonly used in atmospheric chemistry sometimes to track wind patterns. So there you go. Imagine the green one is sulfur and all of the blue ones are fluorines. You got that shape. So can you see the square in the middle? Right? Kind of hard to draw that. So you got the one up, one down. Those are the lines. And then I orient it so that I have the square. So this one right here coming at you, that's an open wedge. This is a dash wedge, open wedge. No, dash wedge, open wedge. Right? If they're coming towards you, they're open wedges. Coming away from you. Now, sometimes you'll see them colored in as a solid wedge. You know, whatever. That's okay. So you have the dash and then the solid, which I don't fill in myself. There you go. Perfectly symmetric. So let's draw our 90-degree bond angles there. You don't have to write alpha equals. You can just write the number. And if they're all the same, you'll only have to do one. Or you can just write all bond angles 90 degrees. I don't care. As long as you notate it, I'm good. Now, what if one of these is a non-bonding group? Notice it doesn't really matter. They're all perfectly symmetric. This is not like a trigonal bipyramid one where you have axial equatorial. The lone pair goes wherever you want it to go. So pick one and show me what that looks like for number 12. All right, let's mess up our beautiful symmetric octahedral shape. So now we got 6 electron groups. 5 are bonding, 1's non-bonding. Right, so it's not going to. You got an octahedral electron group geometry, but not an octahedral molecular shape or geometry. So we're going to stick a lone pair. It doesn't matter where you put it. Put it anywhere you want. They're all totally symmetric. I like to put it on the bottom because it shows the resulting molecular shape or molecular geometry the best. But it's not right or wrong. So you could put it anywhere. So if I have this octahedron, I can pull it out here, pull it out here. I can pull it out here and just rotate it like this. It's hard to see that way. But if you rotate it this way, what's the result that you see? Okay. Do you see the square? Right. So there's a flat square. That's the base of your pyramid. So you have a square pyramid. Right. We've seen trigonal pyramid. Trigonal bipyramid. Now we got a square. We got a square base for our pyramid. Here is at the apex. So that's why I like to put the lone pair on the bottom like that. So Br, bromine pentafluoride, BRF5. So if you do the 6n plus 2 minus number of valence electrons, you get a -4. So you got 2, 4, 6, 8, 10, 12 electrons around it. 5 are single bonds, 1's a lone pair. If you do the Lewis structure, I practice it. If I was you, do Lewis structures and see how I get the VSEPR structure from it. And so when I draw that, I got this one coming straight up, but I've got this one coming at you and this one coming at you. Those are the open wedges. I got this one and this one coming away from you. Those are the dash wedges. So you got this kind of a flat square with a top. Square pyramid. Hey, hey, hey. So you got everything's 90 degrees, 90 degrees, 90 degrees. But now that we have that lone pair, if you went from here to here, it's kind of hard to see. That's 180 degrees. So it's kind of hard to draw. See, that fluorine to that fluorine would be 90. But if you go across the diagonal from here to here, you get the 180 degrees. It's kind of hard to draw that one on there. One more. We're almost done. Add another lone pair. Where do you think that second lone pair goes? So this is no longer symmetric anymore because now that that lone pair's in there, the second lone pair, remember, lone pair is the maximum repulsion. Then lone pair bonding group, and then bonding group is the least repulsion. So lone pairs want to get as far away as they can from each other. So where's the next one going to go? We have reached the end junction for where we're going. All right, 6 electron groups, so that gives us an octahedral electron group geometry. 4 are bonding, 2 are non-bonding. So we got to stick 2 lone pairs on there. First lone pair, wherever you want. Second lone pair wants to get as far away as it can. It doesn't want to go at a 90-degree angle. It wants to go on the opposite side. So you lose your top and your bottom, and you're left with a square, a flat square, which is square planar. See that? With really, really tight 90-degree bond angles. You also have the 180 coming across here, which is hard to draw on that. I tried to get that there. So now a lot of people just flip it and draw it like that. Just draw the square. I just left it from what I had there in the planar position, where you have the two open wedges coming at you, the two dash wedges. But if you want to flip it and just draw 4 lines and make it planar, that's perfectly fine. So you can see the 90-degree angles, and then the 180 going across, square planar. That's it, gang. Those are all the VSEPR shapes you need to know. Work on those. Work on the Lewis structures. This is xenon tetrafluoride. Whoa, noble gases don't like to react, but you get a big enough laser, pow, you can do it. Try it. See how it pans out for you.